Hi everybody, welcome back. So I'm just going to do a little bit of introductory, very simplistic, very just entry level, but it's really important for us to understand the concept of complex numbers. I wish they came up with a different term for them because once we kind of get into it, we'll realize although they can be fairly intricate, the complexity of them kind of makes them a little bit misleading in the idea that they're a lot more challenging than they really are. And you might be thinking, why do I need to understand this for maybe an electrical apprenticeship program? And I'll get into that, but I just want to give a little bit of an introduction to what a complex number, where it came from, like what its root is, and then we'll move forward in the next couple of videos to understand how can we use these to simplify the circuits that we're trying to analyze. So on a Cartesian plane or on a coordinate grid, before you probably would have seen this as an X and Y axis, which there's nothing wrong with that. I like that, the X and Y axis. We call this a horizontal and vertical component. But when we're dealing with complex numbers, what they will relate these to is, this is what we will call a real property of the real number system. And if you're thinking, Jason, how does that relate to real power? Directly to real power, okay? So this is part of our real number system. This is something you could measure, something that you could quantify. If I have a point of origin, I could break this up and I could say this is 1, 2, 3, 4 units, and we could call that a positive value. And now when I'm going in the opposite direction, I've already assigned 1, 2, 3, and 4. So really nowhere else on this coordinate plane can I use these to identify, because 3 has a distinct value from the point of origin. So never again can I use that value of 3 other than anything that would fall on this vertical point. So we have to come up with another way. So when I move, if I'm going to call this a positive value, I could just move in this direction. Call this -1, -2, -3, and -4. And now I have a definitive way of describing in two different directions a place that I am from or a distance I am, or a magnitude that I am from the point of origin. So the idea of complex numbers now, this should seem fairly straightforward. This is just the number line. But getting into the idea of complex numbers, now when I'm moving vertical, or let's just call it up, if I'm moving up on this coordinate plane or down, I don't want to use 1, 2, 3, and 4 again, because we've defined this place along the number line as those values. So this is where, and they came up with this, they invented this system in order to address what if I need to be at more than one plane. So I'm going from one-dimensional to two-dimensional. And really, as soon as we understand the idea behind complex numbers, it was a way for us to solve very, very complex, or very difficult, I won't use complex, very difficult equations by introducing this system, and it actually simplified it a great deal. So now when we move vertical on the same, using the same scale, we introduce what is seen as I. So that would be 1I, this would be 2I, this would be 3I, this would be 4I, and this would be 5I. If I wanted to move down, I could say this was -I, -2I, -3I, -4I, and -5. Now I have a distinct way of describing where I am on my coordinate plane, and at no point would you be confused. So I could move to this point right here, and I could define that place on the number line define that place on the number line as the real number of 3. I'm not up or down, I'm just at 3. So when we're on our vertical, this is part of the imaginary number system. So this is the real number line. This is imaginary. Now, I wish that they came up with an even better thing than imaginary, because we think of imaginary, we think of fake or something like that. It's not at all. It's just a way of describing. If it's not real, it must be imaginary. It's just a way of describing where they are. So if I wanted to define where I was here, I could define that point by its real and its imaginary components. So I could say this lives at coordinate 3 and 3i. I could come to a point down here and describe where I am there by saying I am -1 and -2i. So we can definitively place where we are by using this set of values. And if you'll notice, we will always describe the real first, and then the imaginary will always be second. And you might see this in different fashions. You might see this as something like that. They're using the same convention, just in a different order, but the intention is identical. So if you're thinking, okay, for my program as an electrician, where would this come into play? Well, if we think of an AC circuit, and we'll start with a series AC circuit, and where I would have a resistive component, and I would have a purely inductive component, and let's say that I had, let's put another resistive component in here for now, kind of symbolize a conductor. Rather than building some elaborate diagram, which you've all done, and you all understand that concept, now if I wanted to solve for the impedance of this circuit, and I knew that this was 2 ohms, this was 3 ohms, and this in itself was 1 ohm, when we look at this, we might forget how to add this, right? We might do, oh, it's just 2 + 1 + 3. Ohms are ohms are ohms, and I add them together. But we forget the displacement of this pure inductor. So we can't just add them directly together. And so a lot of times what I will see is something like this. Well, 3 ohms plus 2 ohms plus 1 ohms, you forget what that's doing, and you just add them together to get 6. But we know in reality, I can't directly add them together because it's a different property. Those are 3 different components. I know the displacement. And if you notice, this Cartesian plane, there's 90 degrees. Of course, if we're talking the displacement in degrees, there's 90 degrees between the real and the imaginary. So now, rather than just leaving it at that statement, I can put my I in front so I remind myself. And calculators, they understand this convention. This is very well known. And now when I look at this, I think, oh yeah, right, I'm not going to add that directly together. What is that symbol right out in front? So this is just an example of why understanding how complex numbers, this actually is going to greatly simplify what I need to do. This is easy to compute. It's easy to punch into our calculator. It will recognize it. We don't need to go back to the fundamentals of why that is 90 degrees out. You already know that. But what we're going to address in this next couple of videos here is just how to use this, how to be more familiar with it, and how this will actually simplify what we're doing moving forward. I hope this helps, and I'm looking forward to see you guys in the next one.